Now see, we know that in splatting, we have to convert the 3D ellipsoid into 2D ellipse. That is projecting 3D to 2D, because we throw 3D Gaussians on the screen, and when we will throw, the 3D will become the 2D, the projection of it. So we'll see how we'll do that. So first let us look at the camera projection overview. So in order to render a Gaussian, we must transform it from the real world to the camera, then to the screen. So from word space, we have to transform it to the camera space. So the idea is that, see, the idea is in the word space, we will be having millions of 3D Gaussians. Camera space means from the millions of 3D Gaussians, we will only consider those who will be the part of the screen or who can pass through the lens, just for analogy. So that is the camera space. And once we have those 3D Gaussians, which will be the part of the screen, then we will have to project those 3D Gaussians on the screen. So from word space to camera space to screen space. That is how the projection will be done. So mathematically, the transformation pipeline, it will be something like this. So X screen is equals to P into V into X word. X word is like the 3D Gaussians in the word space. We are multiplying it with the view matrix. View matrix means it will filter, or it will consider only the Gaussians, 3D Gaussians, which can become the part of the screen. So that is the view matrix. And P is the projection matrix. It will project, it will convert the 3D into 2D. And the result of this mathematical operation will be the 2D Gaussians, which will fall on the screen. So we will get screen space. So X screen is the screen space. X word is the word space. P is the projection matrix. V is the view matrix. Now see, the idea is that when we will, like for a 3D Gaussian, when you will be converting that 3D Gaussian into the 2D, like projecting the 3D Gaussian on a 2D surface, you have to project the mean, the center, and also the variance, covariance matrix. So two things we have to do. We have to project the center, that is the mean, and the covariance matrix. So let us understand how we can project the center, the mean. So that is like very straightforward, projecting the center. So to do that, so the center of a Gaussian is projected using standard 3D graphics math like this, wherein phi is like a projection function which will take the center in the 3D space, and it will give us the center in the 2D space, mu dash. So mu dash is the center of the 2D footprint. So it is like a very straightforward transformation. Now, if we talk about projecting the covariance matrix, so it is like bit challenging, because here projecting the covariance matrix means we are projecting the shape and orientation, and it's challenging. It's challenging to project the shape and orientation. So see, we already have a 3D Gaussian covariance. We have it, and we have to compute 2D Gaussian covariance. So for the covariance projection formula, we will be making use of Jacobian. So we will be making use of the Jacobian of the projection function. So Jacobian of the projection function is how the projection function changes by changing the coordinate. Because this differentiation, it is like change of projection function with respect to a small change in the position. That's the Jacobian. Now, why it works, or why we make use of Jacobian? Let us understand that. Let us understand it. See, the idea is that while projecting the shape and orientation, perspective will be a challenge. Because if we don't consider Jacobian, we might get wrong perspective. Perspective Means like the height and all I have to change, because the idea is that a large object in the 3D space, when it gets projected, its dimensions might change. Just imagine the shadow. You might have seen like your long, very long shadow or a small shadow. So when I'm projecting it on the 2D space, this perspective will play a role. And for that to work perfectly, Jacobian is something that will help us. So that is why for this transformation, like for projecting shape and orientation, we have to make use of the Jacobian, wherein Jacobian is considering that into like what Jacobian will be doing is that, because in the Jacobian matrix will be containing the derivatives, which will be containing information that okay, a small change in a coordinate, how the projection is changing, like a small change in x coordinate, y coordinate, z coordinate, how the projection is changing with respect to that, something of that sort. So when you consider Jacobian, the formula you will get is something like this, and this is the covariance projection formula. Like 2D Gaussian covariance is equal to Jacobian multiplied by 3D Gaussian covariance multiplied by Jacobian transpose. So what is happening is that this Jacobian, it will basically scale, or it will take care of that, because see, 3D covariance matrix, it is containing the size, shape and orientation in the 3D space. When I multiplied with Jacobian and the result I multiplied with Jacobian transpose, the result is also a 2D covariance matrix which is containing the information about the size, shape and orientation of a 2D Gaussian in the 2D space. Like the 2D ellipse, what will be the size, shape and orientation of that? That we will get from this formula. So the Jacobian, it describes how small movements in 3D affect screen coordinates. Thus, it transforms uncertainty volumes from 3D into 2D. So that is what Jacobian is all about. And as a result of this transformation, each 3D Gaussian becomes a 2D elliptical Gaussian footprint on the screen. So projecting 3D to 2D is very clear that the transformation pipeline is that from the word space X word, we have to multiply it with the view matrix and projection matrix to get the X screen. So we have to project the center, which can be a normal standard 3D project graphics math, and we have to project the covariance matrix, which will involve the Jacobian matrix.